Very simple setup with a DC power supply, constant voltage set at 2.4 volts, no current, two carbon type electrodes, and at the cathode I have graphite felt. The resistance of the graphite felt right out of the bag, it didn't even clean it with ethanol, is between 5 and 7 ohms over 1 centimeter. I've used this graphite felt over the years, or the past year or two, with success. It's paired with graph oil. No coatings, just as is. And there is no gas evolution at 2.4. It's been running a half an hour. Now I've been up to 2.5, 2.6, 2.7, and then gas evolution. So let me put this now. First of all, I hope you can at least see. There is some adhered gas from when I was finding the water electrolysis Overpotential. Now normally about 1.23 volts is a magic number for those that electrolyze water to produce hydrogen oxygen gases. And of course, researchers know the importance of the oxygen half reaction. It's usually not the hydrogen that's a problem. Now, it's ironic, at least for me, with supercaps, that I'm not trying to lower the overpotential. I'm trying to increase it because I don't want gas evolution. The electrolyte is 3 molar Epsom salt, magnesium sulfate heptahydrate in distilled water, 3 molar. And let me now bring this up. So that's the overpotential effect, 2.4 volts. Now, we're working with modified carbon electrodes. Here we just have graph oil and graphite for demo purposes. Let me bring this up to 2.6. Okay. When you go to 2.6 volts, now you're drawing 10 milliamps. Let's see. Gas evolution is occurring. I hope you can see it. Let me zoom in there. Yeah, sure enough. I'm seeing it, and I hope you are. So I've exceeded the overpotential. And of course, the role of the electrolyte you're using and the electrode composition is very important. You see, I want to use water-based electrolytes in my supercap work. And magnesium is very interesting. And of course, there can be problems with magnesium hydroxide forming a passivation effect on the electrodes. But what I'm doing to try to remedy that is I'm making a composite electrode. So here I have 2 sections of graphite felt, and by brush I'm applying a paste of CMC binder, water, and this is more art than science, getting the right consistency. I like consistency about that of yogurt. And with the binder, I have a small amount of carbon black G, carbon black from gas source, with very good electrical conductivity. And I have the composite along with extra fine sieved activated carbon. And I also have another important component white halloysite. Mine is a gift from Applied Minerals Incorporated in Utah. White halloysite, low or no iron detectable at part per million levels. And we don't want the iron there, but I'll leave that aside in this video, the discussion of that. So it's mold, and it's being applied to graphite. So I'll apply 2 or 3 coatings on both sides. We have a scanning electron microscope, so we'll be studying the composition and the surface situation here. The halloysite is nanotubular. And we will then investigate these electrodes after a number of cycles of charge-discharge. And I can work with the let's say 2.4 volt. That's fine for me because I want to use a water-based electrolyte for cyclic voltammetry. It's going to be a lot easier in some regards when I analyze these composite electrodes. And that's my real focus, getting the right composition here while holding the electrolyte magnesium sulfate heptahydrate concentration constant. And we'll get the Coulombic ratios, milliamp hours for charge-discharge cycles. Hopefully a ratio of 1:1. So it'd be a very high Coulombic efficiency. We'll keep you posted on our work. If you go to ResearchGate, David S. Soriano, you can find some of my preprints there with Supercap work we're doing. Thank you very much for watching. Bye for now.